Okay, so we were talking about the current continuity equations, and it shows how at any particular point in the semiconductor, the electron density varies as a function of time. So, electron density at any point can be contributed by several factors. It can change with respect to time because of several things. For example, it can change because of this thermal recombination generation, or there can be some light which is generating some holes and electrons. They are being generated and then they are recombining. Okay, and then you can also have the change in electron density because of the current. So if there is a flow of current through a point, be it drift current or diffusion current, because of that, if there is a gradient in the current, so that can also build the electron density at a point. If the current entering, say, a small volume is not equal to the current leaving that volume, so there will be some buildup of charge over time. So that will also contribute to the electron density. Similarly, for holes, you have similar terms. So you have gradient of current, you have some contribution from the thermal electron hole pair generation, and then some other contributions such as light. So let's build upon this and okay, so let's talk about minority carrier diffusion equation. So okay, so what are these? So now there can be situations where you know that the electric field is small in your semiconductor region. Okay, and the drift current is not dominating; it's the diffusion current that is dominating. Say you know that the diffusion is dominating. So in those cases, you can derive these minority carrier diffusion equation. You can neglect the drift current and and derive the equations which we call as minority carrier diffusion equations. Okay, so assume that you have a p-type material. Okay, and in a p-type material, say I'm talking about the regions where the electric field is small. Okay, if I have a small electric field, then the total current, which is equal to the sum of drift current and diffusion current, that will be almost equal to the diffusion current because I'm neglecting the electric field. Okay, and if I do that, then my this electron density, which is equal to the equilibrium electron density and the excess carrier density. Okay, I'm talking about a p-type material, so I will talk about minority carriers are going to be the electrons. Of course, delta n will be equal to delta p, but delta n, this excess carrier concentration, will largely affect your n. There will be addition to the whole density also, but whole density is already so large that this addition of delta p will not matter. Okay, so if I have this n equal to n naught plus delta n, then I can simply differentiate because this is a constant. So del n by del x will be simply del of delta n by del of x. Okay, so if I talk about change in the total electron concentration as a function of x, or delta n as a function of x, if I take the gradient, both will be equal. Okay, we then have, so now you can calculate what is going to be your this Jn, right? So Jn is approximately equal to the diffusion current, and if you can take the derivative, so then you will get del Gn by del x term. So why I'm calculating it? Because it appears in the current continuity equations. Okay, and right now it is only contributed by the diffusion current. So if you take it, so there is a derivative of del n by del x already here. Yeah, so so there is a del by del x, and then already you have this del n by wait a minute. Yeah, so if you simply differentiate Jn, so this will become the double derivative. Okay, that's simple. It's coming from here. So this term is the double derivative of the electron density. Okay, now I can plug this thing back into my current continuity equation, and what I get is equal to this um, minority carrier diffusion equation. And I also assume that, say, the injection of these minority carriers, I have low level injection condition. Low level injection condition means your excess carrier concentration is going to be much smaller than the majority carrier concentration. Okay, so if I have, say, delta n, so it's going to be much smaller than the majority carrier concentration in the p-type material, which is p naught, approximately p naught, right? P naught is, say, of the order of, say, 10 to the power 16 or 17 per centimeter cube, and this delta n is only going to be of the order of, say, 10 to the power 10, 10 to the power 12 per centimeter cube. So under those conditions, what I get is, so the thermal, this indirect thermal recombination generation, which is the dominant mechanism in silicon, so that will be simply equal to minus of delta n by tau n, right? Tau n is your minority carrier access time. We have seen this equation last time. Yes. So it's a big, the total expression is a big expression, but if you assume that there's a low level injection, then you can assume that Shockley-Reed-Hall expression, and then you can simply approximate it like this. So we did two derivations, and from both the derivations we got, for the low level injections, this is equals to minus delta by tau. Okay, so we have now everything. So uh, okay, so if we say assume there is some light also, so we can simply call that, say, as GL. Okay, so if I'm shining some light, so there can be some generation and recombination of electrons. So if that is present, so you can add that, otherwise you can leave this term. So after plugging in all the terms in the continuity equations, what we will get is del n by del t will be equal to, what was that, 1 by q del jn by del x, right? So what is 1 by q del jn by del x? So it's equal to this term, so it's here, and then plus del n by del t due to thermal, right, which is equals to minus delta n by tau n, so that's here, plus del n by del t of any other thing. So that can be there, uh, that may not be there. Okay, so if it is there, then it is equal to g of l, plus you can, if you have some other things going on, so then you can add del n by del t due to those terms as well. So this type of equation is called minority carrier diffusion equation. Okay, so there is no drift present, but there is only diffusion. So what does this equation is going to give you? So in this equation, you have the change in the electron density with respect to time, as well as the change in electron density with respect to x. Okay, so it's this equation contains both t and x. Okay, both time as well as position. So if you solve this equation, so you will get a solution which will be a function of both time as well as position. But under certain assumptions, I will show you some exercise examples, and then you will be able to see how we can solve this equation, and under some assumptions you will be able to uh, ensure that this term goes away or this term goes away. So this is going to become only a function of time and x, but in general it's a function of time and x both. Okay, so this is for the electrons in a p-type material. You can have a similar equation for holes in an n-type material. So this is the equation for the minority carrier diffusion. Okay, so let's move. Let's do some exercise. So say I have a uniformly donor doped silicon wafer, and see the wafer is maintained at room temperature 300 Kelvin. Okay, and the full wafer is then suddenly illuminated with light at time t equal to 0. Okay, so there is going to be some generation recombination because of the light. Now assume that this is the doping density 10 to the power 15, and you have been given this minority carrier access time for the hole, because you have n-type material, so the minority is going to be the hole, so that's why they have given it. And a light induced creation of 10 to the power 17 electrons and holes per centimeter cube per second. okay, throughout the semiconductor. So I have a semiconductor wafer, and throughout the semiconductor wafer, uniformly, I am creating 10 to the power 17 electrons, of course, holes, because they will be created in pairs per centimeter cube per second. Okay, and I have to determine what is my delta P as a function of time. So how my uh, whole concentration, excess hole concentration is going to change with time, I have to calculate it. So I'll give you just 2 minutes to think about it, how to approach this, and then I will show you the solution, how to do this problem. So this problem is going to be solved with the help of these current continuity equations. So did I say, first of all, did I say there is any electric field, or I bias the semiconductor? So I haven't biased the semiconductor. There is no externally applied electric field, and it is just one uniform wafer, right? Uniform wafer of silicon, N-type silicon. There is no external voltage, so electric field is going to be zero. Okay, there won't be any drift current. It means, yeah, and you are illuminating the wafer uniformly. So everything is uniform. If it is uniform, there is no gradient, nothing. You don't apply any voltage, and it's just one single material. There will not be any internal internal electric field inside the semiconductor. So that will make this term perfectly equal to zero. So you can apply your minority carrier diffusion equation. So that's the hint. Now after that, what to do, just think about it, how to approach this problem. So you have this equation, right, and think what terms you have been given. So we are talking about this equation because we are talking about holes in an n-type material. So this is the equation you have to focus upon. Okay, so let's try to solve it. Okay, so this is the question we have to do. Okay, so what we have been given a situation like this. So you have a silicon wafer, and this is being illuminated with light. Okay, and this light, we are assuming that it is reaching the whole thickness of the wafer uniformly, and it is creating electron hole pair everywhere in the semiconductor throughout. And what is the rate at which the electron and hole pairs are being created? So the question says that electron and holes per centimeter cube per second throughout the semiconductor. It means your GL, rate of generation because of the light, that is equals to 10 to the power 17 electrons. So 10 to the power 17 electrons per centimeter cube per second. So that's what you have been given. Further, this has been given tau p is equals to what's the value, 10 to the power minus 6, 1 microsecond. Okay, 10 to the power minus 6 seconds. Okay, now what do you do? So you have this equation. Okay, minority carrier diffusion equation. So I have del p by del t is equals to dp into d2 delta p by uh, so this is partial differentiation, del x square plus minus of delta p by tau p, and plus you have this gl. Okay, so this is what we have. Now in this case, of course, let's focus on which terms can be zero or can be evaluated using this situation we have been given. Which of the terms we can say eliminate, or which of the terms can be simplified? So let's focus on this situation. So this is uniformly illuminated by light. It means if there is an excess concentration being created here, The same excess concentration is being created here, same excess concentration is being created here, right? So what will happen? Because the same excess concentration is being created everywhere, and we know that the total concentration of the holes is going to be P naught plus delta P. This is already uniform because the temperature of the wafer everywhere is same. It's held at a uniform temperature. So this quantity P naught is already, which is the equilibrium hole concentration. This is same everywhere. Plus this delta P is also same everywhere. It means P is going to be equal at all points. If P is equal at all points, this term, the gradient of this delta P with respect to x, this is going to go to 0. Okay. Now if this goes to 0, then you are left with this equation, delta P by tau P plus GL. So if you take it on the left hand side, plus delta P by tau P is equals to GL. Now this is the equation you have to solve. Now this is ordinary differential equation, first order differential equation. You can solve it. So this is of the form of this equation, dy by dx is equals to plus some say alpha x is equals to some say beta. That's the form of the equation, right? So how do you solve this type of equation? So what we do, we calculate an integrating factor, right, and multiply on both sides. So how do we calculate that? So that integrating factor is e to the power, what is the coefficient of x? So the coefficient of x is 1 by delta P, and integrated with respect to x, so what you get is e to the power x by tau P. Now let me multiply on both sides of this equation by this factor, e to the power x into e to the power x by tau P. So e to the power x by tau P, del P by del T plus del P by tau P e to the power x by tau P is equals to GL into e to the power x by tau P. So that's what we get. Okay. Now observe this. This is the differentiation of this whole thing, is the differentiation of this delta P. So this is delta P, not T delta P. I should have written, because P and delta P are both equal, so it doesn't matter. I mean, their differentiation, of course, they are not equal. So let me write it like this. Okay. Okay, so this is P or delta P, you can write anything. Okay, so I have this delta P here into e to the power x by tau P. So what will be the differentiation of this thing with respect to time? This is a partial differentiation. So with respect to time, the differentiation is going to be, oh sorry, I think I made a mistake here. So because the variable here is t, so this should be t. This should be t. Okay. Because my x is actually t. There is no x because those gradients were 0. Okay. Now everything is in terms of time. Okay, so if I differentiate it, so how do you differentiate it, right? So differentiate this, right? So that will give you this term, right? This is as it is, plus differentiation of this, so that will be e to the power t by tau P. It will give you this term plus the differentiation of this thing, so that will be 1 by tau P times this, so that is delta of P, right, is equals to GL into e to the power t by tau. So I can write it like this, del by del T into delta P e to the power t by tau P gives me GL into e to the power t by tau P. Now this is very easy to integrate, right? Integrate both sides. So with respect to time, right, both sides are function of time. So I get on the left hand side, it will be simply, because it's a differentiation of this whole thing, I simply get e to the power t by tau P, right? So this is tt, this is tt, is equals to this GL is a constant, I can take it out of the integration, and e to the power integration of t by tau will give me e to the power t by tau P divided by the coefficient, which is 1 by tau P, so that will become into tau P, right? plus the constant of integration c. Okay, so this is the finally the equation that we will get, but we still have to find this c. Now how do we find this c? So you have to use some kind of a condition, some kind of some initial condition, because it's the differential equation we solved was in time. So we need some kind of initial condition. What is happening at say t equal to 0? So what do we have at t equal to 0? Just before shining the light, just before shining the light, there was no light, right? So right, if you plot gl as a function of time, so before time t equal to 0 it is 0, and just after the time t it is a constant value. So this is time. Yeah. So at t equal to 0, just before say t equal to 0, what we have, we don't have any excess carrier concentration. So my delta p is equals to 0. So delta p at t equal to 0 is 0. There are no excess carriers. Yeah. If that's the case, let me call this equation number 1. So put that condition back here. So that will give you what? So this is going to become 0, right? Delta p is equals to 0 is equals to gl tau p. This is going to become equal to 1 plus c. So c will be equal to minus of gl times tau p. Now plug that c back here in equation number 1. So then you get delta p into e to the power t by tau p is equals to gl tau p e to the power t by tau p minus gl tau p. Okay, multiply on both sides by e to the power minus t by tau p. So that will be cancelling this. This will become gl tau p. Let me take it out. That will also cancel it. So that will become equal to 1 minus e to the power minus t by tau p. So this is the equation that you get. So delta p as a function of time is this. Okay, now you have been given this gl, right? 10 to the power 17 per centimeter cube. This is given, so you can calculate what this function is going to be. So how will it look like in time? So at t equal to 0, so this 1 minus 1 will become to equal to 0, and delta p will be equal to 0. That's what we had as an initial condition. What will happen over time? So over time, this delta p is varying exponentially with time, right? As the time increases, this factor is going to reduce. So the quantity that is being subtracted from 1, that will keep reducing. And at t equal to infinity, what will happen? This is going to become 0, and delta p will be equal to gl times tau p. So delta p will approach a constant value gl tau p at t equal to infinity, and it will start from 0. So how will the curve look like? So curve is going to look like this. So finally it will reach this level gl tau p, and it starts from 0, and it will look like this. Okay, that's how delta p as a function of time is going to vary. So as you shine the light, the electron excess carrier concentration, it will start to build, and then it will become a constant after a long period of time. So this tau is acting like a time constant, tau p. It's like a time constant here. Yes, whenever you have an exponential decay or exponential say uh, rise like this, so we have a time constant that will determine how fast it is achieving its final value or how fast it is decaying. Yes, so how fast it is achieving it will depend upon tau p. Then what's the value of tau p? 1 microsecond. So after say uh, 3 or 4 tau p, you would have reached here approximately. Yeah, and within those uh, 3 tau p, there will be a transition. So after say long time t, this becomes constant. And what's the reason? Why does it become constant? When you are shining the light, it's not that you have stopped the photons from coming to the semiconductor. You keep shining the light, you keep throwing photons over semiconductor. and electron hole pairs will keep generating, right? I mean, why this delta P initially it increases, but then it becomes constant? Why? Because when you are generating the carriers, you are also increasing the recombination rate. Initially, you had just thermal generation and recombination. Suddenly, you started to generate more and more electron hole pair, right? So, initially, your concentration of electrons and hole will start to increase. But as you increase your delta P equal to delta N, so this is also going to increase the total concentration of electrons. So, this is going to increase electron concentration, this is going to increase the overall hole concentration. So when you increase the electron and hole concentration, what happens? You have now more electrons and holes to recombine also. Yeah, so you are creating more electrons here and more holes here, so they will recombine more as well. Okay, because recombination rate is, if you remember, it is proportional to n times p. So you keep generating more electrons, but recombination will also start to increase, and after some time, so this is your steady state. Okay, steady state is after a long time you will achieve a steady state after long time. So in the steady state, your generation rate GL will become equal to recombination rate, and delta P will cease to rise further, will become constant. Okay, so this is the type of question that can be asked in the assignment or even in exam. So please practice such questions. Not a very difficult one to solve. So usually you will always run into some kind of some exponential whenever you are solving such an equation, because you will have some kind of a scenario which will simplify your this differential equation a lot. So this, although it has these double derivative term and also time, but usually either this will be gone or this will be gone depending upon what you have been given, and then you can solve this differential equation. Usually the solution is going to be some kind of an exponential rise or exponential decay. Okay, so let's move further. So we have this minority carrier diffusion equation and we have done some exercise. Now let's talk about the steady state. Okay, let's talk about the steady state expressions. So steady state means that nothing is changing with time. If you have electron concentration, it's not changing with time. If you have hole concentration, it is not changing with time. So that's your steady state. Okay, so in the steady state, what's going to become zero? What's going to become zero? So did the question we just solved, was that the steady state? No, that wasn't the steady state. In that, your delta P was changing with time. Yes, after long time you achieve the steady state. But now let me talk about that part. After long time, what's going to happen? So in that particular question, I did not have any gradients. So your delta P simply became equal to GL times tau P, because the gradient was gone and the time is gone because it's steady state. But in general, the gradient may not be gone. Gradient can be there. So in the steady state in general, so the time derivative will always be zero, but the x derivative, the position derivative, that may not be zero. And if we just assume that there is only thermal recombination generation, there can be some light also. I mean, so if there is a light, so you can just add that. If there is no light, then that's okay. So if we assume that there is only thermal recombination generation and no else mechanism, so then you will get from the current continuity equation this del 2 delta n by del x square will be equal to delta n by dn into tau n. So where is this coming from? It's coming from this equation. So if you make this term equal to 0. This is not there, so then dn into del 2 delta n del x square will be equal to delta n by tau n, and then you can take dn in the denominator, right? So you will get the expression I was showing you. So this expression. Now delta n by dn into tau n. So what's the dimension of this thing, right? So this is del x square here, so it should be some length square. Okay, it has to be some kind of a length square here. So let me call this dn into tau n as some kind of ln square. Okay, ln square. So ln is then under root of dn into tau n. Ln is called electron diffusion length. So you can physically think of electron diffusion length as uh, it's like a, if you have a say minority carrier electron in say p-type material, and you leave the electron into the sea of these all majority carrier holes. So after a particular distance, your hole is going to recombine with the electron, right? Some of the electrons will recombine very early, some of them will combine later, right, at a larger distance. So every electron will recombine say at some different distance, and mean of all of those distances is basically your electron diffusion length. Okay, so it's the distance, the average distance after which your minority carrier, which is electron in this case, will recombine with the hole, the majority carrier hole. Similarly, we can have minority holes, the equation, steady state equations for minority holes in an n-type material. So for that case, what we get is del 2 into delta p by delta x square is equals to delta p over dp into tau p. So let me call this as some lp square again, and lp is going to be the hole diffusion length. So it's the length after which a hole is going to recombine with the electron, majority electron. Okay, now I have these equations, and these equations are solvable. So we have done such exercise uh, when we were solving the Schrodinger equation. So we have seen this thing many times, right? So there used to be d2 psi over dx square is equals to some some k square into some kind of uh, psi, right? So that type of equation we have already solved so many times. So in this case, that coefficient, that multiplication factor, which used to be k square, in this case that is 1 by del n, 1 by ln square. So how do I solve this equation? How do I solve this equation? So it's very simple to solve. So you can, you know, okay, let me show you. Okay. So you have this d2 delta n by del x square is equals to delta n by ln square. Just take it on the left hand side, equals to 0. This is the equation you have to solve. So you have del by del x of, like, let me call this as an operator d, right? So you have this d square delta n minus delta n by ln square equal to 0, right? And you can calculate d square minus 1 by ln square delta n equal to 0. Now you can calculate the solution of this. So solution of this is going to be some kind of delta n as a function of x. It's going to be some a into e to the power what, minus of x by ln plus b into e to the power plus x by ln. Yeah, that's what we used to get. So there will be two solution plus 1 by ln minus 1 by ln, and then you can have a solution like this. So which one of these term is going to survive? So now I know that if I have a delta n, because of, say, some generation. Say this is some kind of a semiconductor bar, right? And this is x equal to 0. And I shine some light here and I switch off the light. After I switch off the light, what will happen? This is going to, so you have a lot of concentration here. Say, let me call that concentration as some delta n 0 at x equal to 0. And then you have a decaying, an exponentially decaying concentration. And because the length of this bar is assumed to be, say, small, or assumed to be very large, so at x tends to infinity, as x tends to infinity, your delta n should tend to 0. Okay, now look at this solution. I know that at x tends to infinity, delta n has to be 0. If I choose this term to be present, if I assume that, say, this b is finite, then e to the power at infinity, this term is going to blow up. Okay, because this term is going to blow up, so this delta n will become infinity, and that's clearly not this is clearly not what happened. Okay, at x tends to infinity, delta n will decay to 0, not it will not become infinity. So this b has to be 0. Okay, so then we are left with this delta n x is equals to some a into e to the power minus x by ln. And I know that at x equal to 0, my delta n is some kind of delta n 0. So delta n 0 will be equal to a, and put x equal to 0 here, so that will become equal to 1. So a is your delta n 0. So now the plug this a back in this equation, so you get delta n as a function of time is as some delta n 0 into e to the power minus x by ln. So this is the solution, and it correctly represents this picture. This is the picture that we expect it's going to happen. We don't know it's exponential or not, but we definitely know that if you have some kind of a finite concentration here, it will decay to 0 at very large distance. And this is what my expression is showing me. At x tends to infinity, this expression is going to become equal to 0. At x equal to 0, this is some finite value delta n 0. Okay, so we are then going to get the solution like this, and so this is a mistake. See, this should be delta n here, okay, because we are talking about minority holes or minority electrons. So what we get is this delta n as a function of x is equals to this quantity. Similarly, if you have holes in an n-type semiconductor, so you get this exponentially decaying profile. Okay, so we have seen now the variation of excess holes and electrons with respect to time as well as with respect to x. So the earlier question that I gave you, that was with respect to time, and this is with respect to x. Okay, so this is another exercise. You can check it and how to approach this. So say I have a silicon bar, and at x equal to 0, I shine light on one end of this bar at x equal to 0, and I'm assuming that this does not penetrate much into the silicon bar. It's mostly at the surface. So whatever generation is happening, it is not happening throughout this silicon bar. Actually, what happens whenever you shine a light on a material, its intensity decays exponentially. So as you go to larger and larger distance from the surfaces, the intensity of light keeps decreasing exponentially. And similarly, the generation rate also decreases exponentially. In this particular silicon bar, that decay of the light happened within a very small distance. So mostly the surface has the generation, but the whole silicon bar is not having any kind of uh, generation because of the light. Okay, so I shine this light, right? And we know that whenever we shine the light, so what will happen? what will happen if I shine the light? First of all, there will be an increase in the excess carrier concentration. So what kind of silicon bar we have? So we have a silicon bar with n-type doping. So holes are going to be the minority carrier. So first there will be an increase in the hole concentration. Excess hole concentration will increase here with respect to time. Yeah. So something similar to what I showed you. So something similar to this. So I have this delta P at x equal to 0. This will increase with time. Okay, it's going to increase with time, and again it will eventually become constant. So this is the steady state. Yeah, and steady state, it has a value of gl into tau p. We know that after a long time. So this is the situation we have been given. Now we are not starting from here, we are starting from somewhere here. This is our starting point. This is what we are calling as some time t equal to 0, not this point. Okay, so this is our initial point, right? And I keep shining the light. So if I keep shining the light, my delta p is going to be maintained. My delta p is going to be maintained at the surface at least. So this surface has a delta p equal to some gl times tau. So what is it? So it's tau p, gl times tau p. Inside this I don't have any light, so my gl is 0 here. Okay, gl is 0 here. And because I want to determine delta px and there is no time information, so the question is asking me what is my delta px in the steady state. If you haven't been given any time related thing, right, and they are asking you to plot delta p as a function of x, so it means they are asking to do it at in the steady state. So in the steady state, my delta p divided by delta t, that will be 0. So continuity equation is going to reduce. Yes, so how will my continuity equation look like? So what do we have here? So we have this thing, right? And we just in fact saw what happens in the steady state. So in the steady state, this becomes equals to 0. Okay, and what are you left with? So because you don't even have gl for most of your x, gl is only at the surface, so I can assume this term to be 0 as well. So you are left with this. If you are left with this, so this is exactly the same thing that we saw in the last slide. This thing. Okay, now with the help of the boundary conditions you can solve it. The boundary condition is going to be at x equal to 0, you have some delta p 0. And what is the value of this? What is the value of this? So this is the delta p that you obtained after the steady state, and the value of this is gl into tau p. And what about this? So after applying the boundary conditions, we get this exponential. There were two exponential, but after applying the boundary condition, we know that this b is going to be 0 because the semiconductor bar is long. So I can assume this to be equal to 0. So this is the only term that I will have. So e to the power minus x by lp. So what is lp? Lp is also a constant that can be calculated from here. dp into tau p under root of that. But I don't know the diffusion say constant. So what do I do? So I can also calculate the diffusion constant from the Einstein relation, right? So remember dp by mu p is equals to kt by q. So if you know the whole mobility, which is around 450 centimeter square, centimeter square per volt second, something around that number. I'm not talking about transistor, right? I'm simply talking about a semiconductor bar. So in that, your whole mobility is going to be, for say 10 to the power 15 per centimeter cube doping we have, for those kind of doping it's going to be around 450. So with that you can calculate your lp, okay, and plug in here. and then you can plot this thing. And how will it look like? It's going to look like some kind of an exponential decay. And how rapidly it will decay will depend upon LP. Yes. So it will decay like this. So instead of delta n, we have delta p here. And after a few LPs, say this is LP, this is LP. Say after 3 LP, this is almost going to become negligible. 3 4 LP. Okay, so this is what this is the meaning of your diffusion length. Average distance after which there won't be a minority carrier. It will recombine.